Welcome back to statistics. In this video, we're going to discuss a way to measure spread about the mean of a distribution. The measure of spread we'll talk about is called the standard deviation, and it's a very common way of quantifying the amount of variation in a distribution. The larger the standard deviation, the larger the variation. So let's take a look. So as I said, standard deviation measures spread around the mean of a distribution. There's actually another measurement as well called the variance that's very closely related. The standard deviation, in fact, is the square root of the variance. We'll talk about both because variance is kind of a step on the way to computing standard deviation. But the bottom line is we'll mostly use standard deviation rather than variance. So the variance of a data set is the quote-unquote average squared deviation of the data around the mean. The reason I put the quotes on that is because of the formula you see here. S squared is the variance, and it's an average. Usually when we think about averages, we see a 1 over n, where n is the sample size. Here it's 1 over n minus 1, but the idea is the same. This is still to be thought of as an average. The reason it's an n minus 1 rather than an n has to do with something called the unbiased nature of the statistic we're after here. And we'll talk about that later. But for right now, you should really just think of it as an average with a little tweak. So the variance is the average squared deviation of the data around the mean. And then the standard deviation is just the square root of the variance. So let's see how this works with an example. I'm showing you a dot plot of 5 data points here. These are measurements of the amount of time in minutes it took 5 school children to solve a certain math problem. So we have 2 data points, 2 measurements at 3 minutes, 2 at 4, and 1 at 6 minutes. To begin computing the standard deviation, we're basically going to need the mean because standard deviation does measure spread around the mean. So I've gone ahead and put that up here. If you just calculate that mean, you find out it's 4. So there it is. Now, I'm marking the mean here on the plot because that's sort of the balance point of the distribution, and everything is going to be measured relative to the mean. So I've got a table here where I've just got my data values. I'm calling those X. So you see the 2 3s, the 2 4s, and the 6. The very first thing you do in computing standard deviation is compute the deviations of each of those data points from the mean. So that's symbolically denoted by this X, which means our data, minus X bar, which of course means the mean. So those are our deviations from the mean. And all you do is you take each data point and you subtract the mean from it. So there, I've done that. Those are our deviations from the mean. Now, if you're thinking about measuring spread, one obvious idea comes to mind. Hey, these are the deviations around the mean. Why don't we just take the average of those? That would be the average deviation around the mean. Wouldn't that be a pretty good measure of spread? Well, it sounds good to start with, but if you try that, you notice something kind of unusual. If you add up these values, the deviations, you get 0, right? The negative deviations are canceling out the positive deviations. That is actually going to happen not only with this data set, but with any data set you look at. It's just a mathematical fact that if you calculate deviations around the mean and then sum up all those deviations, the negative deviations are exactly going to cancel out the positive deviations. That's because the mean is the balance point of the data. And it kind of makes sense that some data is going to be to the left of the mean, some data is going to be the right of the mean. but because the mean sort of is what it is, those left-hand deviations are going to exactly cancel the right-hand deviations. So, although it was a good idea, just taking the average of the deviations isn't going to get us anywhere because we'd get zero no matter what our data set is, and that's not a very good measure of anything. One way you could fix this is by just throwing away the negative signs and then taking the average. And that's actually a real thing. That's called the average absolute deviation from the mean. We're not going to use that. It's used sometimes, but not very often. But we're going to do a similar thing. We're going to throw away the signs just by a different method. What we're going to look at are the squared deviations from the mean. So that's what I'm denoting here. You see my deviations from the mean and then squared. The advantage of that is that by squaring, all the negative signs go away, right? And so the squared deviations from the mean are all going to be positive. And that's going to be the basis on which we start doing our averaging. The sum of the squared deviations is no longer going to be zero. There's no negatives to cancel anything out. And as we said before, the variance is the quote unquote average squared deviation from the mean, where in the average we use one less than the number of data points we have. And so again, that's why you see the n minus 1 there. So the variance of this data would be the sum of the squared deviations, which is 6, divided by one less than the sample size. So it would be 6 divided by 4, or 1.5. That's the variance. That is a measure of spread. But as I said, mostly we'll be looking at the standard deviation, which is the square root of the variance. So the standard deviation of this data set would be the square root of 1.5, which turns out to be 1.2247. So these 5 children completed their math problem in an average of 4 minutes, but there was spread around that average, and we measure that spread with the standard deviation now, which is 1.2247 minutes. So a few facts about standard deviation. We always denote it by S, and S is always greater than or equal to 0. That's coming from the squaring, right? That got rid of all the negative signs, and then you start averaging. That's still never going to turn anything negative. The larger S is, the more variation there is in the data. And if S turned out to be 0, that would mean there's no variation in the data. All the data would be exactly at the same value. And then finally, the units of S are the same as the units of the data. So, but going back to our test times here, the standard deviation of 1.2247 is in units of minutes because our original data was in units of minutes. So, how does standard deviation sort of play into a graphical representation of a distribution, like a histogram? Well, here's a histogram of heights of men, and you see the mean there is 69.676, and the standard deviation I've calculated using software. This is a large data set. It turns out to be 1.904. The units of height here are inches, and so the units of standard deviation are inches. The standard deviation is about 1.9 inches. So we could say that in this sample, men on average had a height of around 69.7 inches, but it varied with a standard deviation of about 1.9 inches. Now, to sort of see this graphically, you can put a, let's see, can you see that? You can put a sort of a balance, a fulcrum at the mean there of 69.7, and I've done that. And then I just kind of drew a vertical line above that to put my X bar sort of on top of the histogram just so we could see it a little easier. So there's our X bar. What's done a lot of times is that you simply look at one standard deviation to the left of the mean and one standard deviation to the right. So I've sort of marked that off here. The vertical line there on top stretches from the mean minus one standard deviation to the mean plus one standard deviation. And so that the width of that little line there gives you some idea of a measure of spread. Again, it's 1.9. But you as opposed to the quartiles or and the interquartile range, you really can't say that 50% of the data lies within one standard deviation of the mean or anything. That would depend on the distribution and a bunch of other things. In some special cases, you can make statements about what percentage of the data lie within one standard deviation of the mean, two standard deviations, and so on, although those numbers usually don't turn out to be 50%. So this is a little different measure of spread than the IQR, but it's different, but it's measuring the same thing, just kind of differently. So there's a picture of how standard deviation kind of stacks up with that histogram. Here excuse me, here's another one. This is waiting times in checkout at a large department store. The units are minutes here. It's a really large data set. I think there's 10,000 measurements in this data set. The average waiting time was essentially 3.5 minutes, 3.5 minutes, but the standard deviation was about 2 minutes or 2.1 minutes rounded to one place. You can see that this distribution is right skewed, and that's the way a lot of distributions are. We can go ahead and put a picture up about how the mean and standard deviation sort of play into this picture here. There you see I've got my little fulcrum again, and I've raised x bar up to that point, and then I've gone one standard deviation to each side of x bar. Notice that in drawing this kind of picture, plus or minus one standard deviation, it really doesn't take into account the skewness of the distribution. And on the other hand, the other measure of spread that we've discussed, the interquartile range, does. And so that's one difference. Standard deviation is really more sort of ideally suited to symmetric distributions. And in fact, that brings me to my next slide. So we now have essentially two different measures of center and two different measures of spread. So how would we use those? Well, the basic idea is that you would use the two-number summary, consisting of the mean and the standard deviation, to numerically summarize symmetric or roughly symmetric unimodal distributions. That's sort of what they're best suited for, the mean and the standard deviation. One reason for this is that we already know that the mean is already strongly affected by outliers and skewness. We've seen that in examples. You shouldn't be surprised to learn that the standard deviation is also strongly affected by skewness and outliers. The standard deviation incorporates in its own calculation the mean, and the mean is already affected by outliers. So it's not surprising that the standard deviation would be as well. So that's why we prefer to use the two-number summary, mean and standard deviation, for symmetric and unimodal distributions. On the other hand, the five-number summary and the associated box plot we've seen is a good way to sort of quantify the shape of a skewed distribution. So we prefer to use the five-number summary, minimum, Q1, median, Q3, and the max, to numerically summarize a skewed distribution. I encourage you to play around with some of these concepts, particularly using the SALT tool that we have. In fact, let me just kind of give you a quick tour of that because it really helps to get an idea of how these things work. Here, you can always get to SALT from our Canvas page right there. It's right above the course summary. And I've loaded in a data set here that is the weights of abalone. Abalone is a type of saltwater snail that's considered a delicacy by many people. Here we're looking at a histogram of the weights of them. And you see it's a right skewed distribution. And down at the bottom there, you can see a summary of some of these uh, statistics we've been talking about. The mean, 0.8287, and the standard deviation here is 0.4904. And then also over here, you see the 5 number summary. Notice that Q1 is 0.4415, Q3 is 1.15. So the IQR here would be about 0.71 or something like that. Compare that to the standard deviation. The standard deviation is about 0.5 and the IQR is about 0.7. Now, both of those are measures of spread. They're just different measures of spread. And for this particular distribution, we would prefer the IQR, not because it's more accurate or anything, but just because it's more suited to this type of distribution, a skewed distribution. And but you can compute the standard deviation and the IQR for any distributions, and so the tool goes ahead and does that for us. Okay, so we've now discussed the standard deviation and its use as a measure of spread. I hope you found this video helpful. Take care, and we'll talk to you again real soon.